Hey everybody, Dr. White here with the beginning of our study of areas underneath curves in calculus. We're first going to talk about just how you might compute the area underneath a curve over the x-axis and why that's important. But before we begin that discussion, we need to do a little bit of a warm-up to make sure you know some math notation called summation. So say you need to write out some pattern sums. For example, what if you need to do the squares of the first 5 whole numbers and add them together? You could write them like that where I've got it shaded, you know? Or what if you needed to add up the odd numbers from 1 through 13? You could write them out like that. Or what if you need to do the sine of pi over 4 plus the sine of pi over 2 plus the sine of 3 pi over 2 plus the sine of pi? And so you'll notice your angle in radians is going up by pi over 4 each time. You could write it like that, but this can get kind of tedious. Is there a way to write down things more compactly? You're going to want that if you're adding up more than just a few things. What if you're adding up 40 or 100 or even an indefinite number of terms? There's got to be a shorter way to write out a patterned summation. So let me show you how we do it in math. So this notation here stands for that first sum. The capital sigma here, Greek letter, just stands for summing up. And what you've got on the bottom is what we call an index. A summation index is what the book calls it. Some people call it the index. Some people call it just a dummy variable for reasons that we'll see. And that index starts out at a particular value. And it's going to step through different values starting from the 1 until it gets to a 5. The understanding here is that it starts at 1, then goes to 2, then 3, then 4, then 5. If they don't tell you otherwise, it moves along by 1 unit each time. And then after the sum sign, inside of it, as it were, is what we call the general term. It's the pattern of the summation applied to the index. So I squared. So the recipe here is that you set I to 1 and you compute your I squared, you got 1 squared. Then you set I to the next number, 2. And then you work with your I squared and you get 2 squared. And you keep going that way until you've written down your 5 squared. At that point, you have reached your upper limit on the summation, so you stop. So that's how summations work. Why do we sometimes call the I a dummy variable? It's because you didn't have to use an I to express the same sum. You could have used another letter, like how about a J? This summation still works out to the same sum. So it's called a dummy variable, maybe from the expression any dummy will do. So the key to figuring out how to write a long sum compactly with summation notation is to really figure out the pattern, because the pattern's going to give you that general term, and from there you'll usually be able to figure out the starting points and the stopping points on your index variable. So, if you had to add up the odd numbers from 1 to 13, I here would be the wrong pattern, because if I goes from 1 to 13, you'll catch all the numbers from 1 to 13, not just the odd ones. So you really have to think, what is an odd number? Well, an odd number is one more than an even number, would be one way to put it, or one less than an even number. That would also be a way to put it. And so when you think about it like that, even numbers are twice a number. You could come up with a pattern for an odd number. How about 2i minus 1? So I'm just choosing an index. I said I'll choose I. I make a pattern for an odd number 2 times I minus 1. Once I've chosen that as my pattern, then I can think, where do I need to start my I so as to catch the first number in the sum? I need to start the I at 1 to get 2 times 1 minus 1 working out to the 1. And then when I moves up to 2, I'll have 2 times 2 minus 1. That's 4 minus 1, that's 3. That's the next element. To capture that 13, I would need 2 times 7 minus 1. So I know to stop my summation at 7. So if I choose my pattern to be 2i minus 1, I get 1 and 7 as my starting and stopping points. I could have also thought of an odd number as twice a number plus 1, one more than an even number. That would also be okay. But if I use that pattern, I need to start and stop at a different place in order to capture that same sum. So it's not going to matter when you set up summations. It's not going to matter exactly how you choose that pattern. But once you choose that pattern, you got to stick with it when you're thinking about your upper and lower sums. It's also not going to matter what you choose as your dummy variable. But once you've chosen it, stick to it. This last sum can be written out as soon as you realize the pattern for how to make things go up by pi over 4. And one suggestion for that would be to do pi times I minus 4. Because every time you increase the I by 1, you would be multiplying by an extra pi on the top, thus a pi over 4 total. It gets added on. And so if I think of my pattern like this, then going from 1 to 4 will do. Let me check. What if I got I as 4? I'd have pi times 4 over 4, and sure enough, that does end me up at the pi. Now, sometimes you don't have a definite stopping point in mind when you do a summation. So, for example, you might sum I goes from 1 to n, 2i minus 1, but not really know where you plan to stop right now, and so you might just stop at some number I equals n. And so when you write it out, you would just write out of the first few lower i's until people get the pattern. Then you would do a plus and then do ellipses, dot, 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 indicating there's a lot more in between. And then maybe write down the last term when the index variable is equal to that top number. Sometimes you could write down the second to the last and the last or something like that in order to give people a better idea of what that sum really is. Here's a little exercise, test our understanding. How would you express this sum? So it's an alternating thing. Positive number minus a number plus a number minus a number and so on. And there's definitely a pattern of 1 over bigger and bigger integers. So how could we do it? I'm just going to show you and then explain how I thought about it. I say this works. How come? Well, when I is 1, then I'm looking at a 1 over 1 here, which is a 1. And this bit would be minus 1 to the 1 plus 1, which is minus 1 squared, which is a 1. So I'd have a 1 times a 1, making a 1. Good. Okay, what about when I is 2? Well, then, for the minus 1 to the I plus 1, I'd have this. And when you cube a negative 1, you're going to get back a negative 1. Times a 1 over 2. And so I do indeed get a minus a half to add on. And similarly, all the way up to I equals 6, this works out. So this is a nice thing to remember. If you need your sums to alternate positive to negative, try a minus 1 to your index variable, or a minus 1 to your index variable plus a 1, depending on which one you want to start with, a positive or a negative. You'll always have to think it out each time you set up a sum, which one's going to be the right for you. Some of these indefinite sums with simple patterns, actually there's formulas for what they would add up to, what we call closed form formulas. So, like take the sum of the first capital N whole numbers. So it can be written in summation like shaded. It can be written in what we call non-closed form with the ellipses indicating all the stuff in the middle, like this. But guess what? There's a closed form expression for it. Capital N times capital N plus 1 over 2. If you sum up the first capital N squares of whole numbers, like this, that has a closed form as well. And those are pretty commonly met with. I'd recommend going ahead and memorizing them if you have not met them before. There's another one that's cool, the sum of the first capital N cubes. And it turns out to be the square of the sum of the first capital N whole numbers. Interesting pattern. There are formulas for the sum of the first N fourth powers, fifth powers, sixth powers, and so on. But we just won't show them here. But those are the three that we might use from time to time. I can't resist stopping to prove at least one of them. Let's do the sum of the first N whole numbers. Let's prove number 1 here, okay? So here's a way to do it. Write down the sum you want across a row. Write down that same sum one row down, but in the opposite order. And then add up everything that you see here. But don't add it up by rows because we don't know how to add up the rows yet. Add it up by columns. Add up the things in this first column. Don't you get N plus 1? Now move over to the second column. You have increased the top row by a 1. You've increased what's on the bottom row. You've decreased what's on the bottom row by a 1. So you haven't made any change in the sum. It's still N plus 1. Moving along to the third column and the fourth column and each subsequent column, every change you make decreases the top by 1, increases the top by 1 and decreases the bottom by 1, thus not changing the sum of the column. It's N plus 1 every time. So what do you got there for that total? You've got N plus 1s because you have N columns. But that is twice as much as the sum that you wanted, you know? So the sum you wanted must be half of the N times N plus 1. Great proof. Okay, so that's our summation warm-up. Let's get to the main idea of this section. Areas under the graph of a function. Like take the function f of x equals x squared. So here I am looking at its graph, y equals x squared. Here on the xy plane, it's this curve here at the top. Now I'm only showing it from x is 0 to x is 2. But I'm interested in what's the shaded area underneath that graph. Could we find that area exactly? Well, I don't think we can find it exactly right away, right now, but maybe we could approximate it. Because when I think about it, like finding areas, basically the only thing I really know how to find the area of is a rectangle. Base times height, you know? Turns out any other area that you want to find, you've got to somehow break that area up into a bunch of rectangles and get the areas of the rectangles. That's how you get the areas of other figures. Let's try it here. What I'm going to do is I'm going to take the real numbers from 0 to 2 on the x-axis, that whole interval, that closed interval from 0 to 2. And I'm going to break it up into 4 equal-sized pieces. Capital N equals 4 divisions, okay? They're all equal-sized, and so each of these widths, this one and the other 2, that come between the numbers that you get when you break 0 to 2 into 4, each of those has to be the same, and it makes sense that it should be the whole interval, and the width of that whole interval is its higher point minus its lower, that would give the width, divided by how many divisions. So this time that would be a 0.5. That would also explain why your division points go 0 to 0.5, 0.5 to 1, 1 to 1.5, and 1.5 to 2. They go up by this amount. Let's call that amount delta x. Delta is the Greek letter for D, and in math, delta stands for change. So it's how much x changes as you go from one side of a division to the other side of the division. Now, given those divisions on the x-axis, which I've written down again here, and writing in your curve y equals x squared, construct over each division a rectangle. The division is going to be the base of the rectangle, and we're going to go to the right-hand side of each base and go up to the curve until we hit it, and that'll be the height of the rectangle we make. So, for example, this first rectangle, notice that its height is going to be the height of the curve above x is 0.5. What would be the area of that rectangle? Well, I figure it's the base, delta x, times the height, but our curve is y equals x squared. The right-hand endpoint is a 0.5, so 0.5 squared. Next rectangle. Well, it's also going to have a base of 0.5, but you can see its height is going to be the square of the right-hand number 1. Sorry about that, I accidentally selected the whole thing. So anyway, I'm writing that as height times base, 1 squared times 0.5. Similarly, 1.5 squared times 0.5 gives the height of this rectangle, and the height of the final rectangle would be the square of 2 times the base. So that whole sum right here is written R sub 4 for short. 4 divisions. R means I use the right-hand endpoint of each base to construct my rectangle height. 4 rectangle areas added together. The areas of those rectangles could be used to approximate the area under the curve. It's obviously going to be an over approximation because these rectangles kind of slop over the curve. Each one of them does, so their sum is definitely going to be too big. But we can find the sum anyway. Before I find it, I'll notice that in the sum, 0.5 is a common factor, so I can factor it out of the sum. And I'm going to go ahead and write the remaining stuff using summation notation. What's my plan? I need a general term. Well, to get a general term, I'm going to have to think kind of carefully how things got set up. So let me go back to the interval from 0 to 2. And let me just write the 0 as x0. And then each subsequent endpoint is x subscript a higher number. By the time you get to the end point of your interval will be x sub however many rectangles I'm using to make my sum. 4 rectangles, x4. So if you think about it, this 0.5 here was x1. This 1 here was x2. The 1.5 was an x3. And the 2 here was x4. You're squaring each one, so your general term could be written xi squared, where the index variable is an I, and the I goes from 1 to 4. However you choose to write it, it's still nice to find it. And so I just went to a calculator and I got 3.75. I'm going to write this sum a little bit more generally because I'm thinking ahead to doing this for any function, not just y equals x squared. So I'm going to write f of xi, where in this case, f of x is x squared. And I'm going to go ahead and write the 0.5 as the delta x, how wide each base is. In general, if you're looking at any old graph, y equals f of x, where the f of x stays above the x-axis, and you start in the old place, x is a, end up at any old place, x is b, and you want the shaded area underneath, so where I'm kind of waving my cursor. You could approximate it using these right-hand rectangles. Your approximation will be called r sub capital N if you use capital N of these rectangles. And the general way of doing it is that, capital N instead of a 4. So remember, that's done with n divisions. That delta x is always the width of the entire interval that you're working with on the x-axis divided by how many divisions you wanted to make. Also want to say a bit more about those xi's. The x0 is always the beginning point, so here a. The next one, x1, is the beginning point plus a delta x. The x2 is going to be another delta x added on. So that would be like a plus 2 times delta x. In general, xi would be a plus I times delta x, all the way until you get to the xn. And that'll be a plus capital N of those delta x's. Capital N times this, the capital N's would cancel. A plus b minus a would make b. So the xn is always the endpoint where you end up, just like here the x4 was where you're supposed to end up. Of course, you could make another choice about how to build your rectangles. Like maybe you could make the height of each rectangle be determined by the left-hand side of each base. So look at capital L4 here. 0 squared times 0.5 is the area of this degenerate rectangle that I show here, which is just that line on the x-axis from 0 to 0.5. Its height is 0, its base is 0.5. And I'm thinking of this height of 0 as the number 0 squared. Notice 0 is the left-hand endpoint. 0 squared makes 0. I'm following the idea of making my rectangle's height be up to the height of the function. It's just that the height of the function at 0 is 0. Oops. This next rectangle is determined by the left-hand endpoint. Its height is going to be 0.5 squared. Again, its base is 0.5. Similarly, we'll have a 1 squared times 0.5 and a 1.5 squared times 0.5 to catch these last two rectangle areas. So if I were writing it out in sum notation, I could go ahead and factor out the delta x, the 0.5. And I'm still going to use xi squared as a general term, but I need to change the limits on the I because I'm starting with the x0 and I'm only going up to the x3. And so more generally, you would write this as f of xi, but I goes from 0 to 1 less than the number of rectangles you're making. Turned out to be 1.75 this time. And you can see this time that's going to be an underestimate of the area underneath the y equals x squared curve because the rectangles are underneath. So here's a general formula that you can use to set up left-hand endpoint rectangle approximations to the area underneath the curve. One thing that we've noticed here, x squared is an increasing function. It rises as you go to the right. So your left-hand rectangles are always going to lie underneath the curve, and your right-hand rectangles will always lie over. So the actual area underneath the curve would be between a left-hand and a right-hand approximation, if f is increasing. If f is decreasing, it's the other way around. There are infinitely many choices that you could make for how to set up the heights of your rectangles. I'm only going to show you one more. It's quite popular. It's the midpoint approach. What we're doing here with our 0 to 2 is we're keeping the same xi's. x0 is 0, x1 is 0.5, and so on, because we're still dividing into 4 pieces with a delta x of 0.5. But we're not going to use the left hand, and we're not going to use the right hand. We're going to use the midpoint of each base. So for example, from 0 to 0.5, we're taking the average of 0 and 0.5. We're taking the x0 plus the x1 divided by 2 to get right in between. That gives us a 0.25 right here where that little hatch mark is. Similarly, the 0.5 plus the 0.1 over 2, the x1 plus the x2 over 2, 0.75 if you like, is what we'll use to get the height of the next rectangle, and so on for the other two. So written out numerically, it's like this. On a calculator, it comes out to this. In terms of general terms and summations, here's your delta x times the sum from 0 to 3, xi plus x sub I plus 1 over 2 squared. So for any number, capital N, of rectangles, the midpoint approximation could be written like I've shown there. Anyway, this time each rectangle partly slops over and partly slops under the curve. So they kind of cancel out. Each rectangle kind of cancels out its own areas a little bit. It cancels out its own areas. It cancels out its own errors to some extent. So I think that this is probably the best approximation to the area under curve we've seen so far, this 2.625. You can't say for sure whether it's bigger or smaller. That depends on, the nature of the curve that you are approximating. But there's a great theorem. Wish we could stop to prove it, but it's actually several years ahead of y'all for you math majors. If f is continuous on that closed interval, meaning if you could draw its graph without lifting your pencil, no jumps, no holes in the graph, then doesn't matter whether you work with right hand or left hand or midpoint approximations. The more rectangles you use, the closer the sum of the areas is going to be to one fixed number L. So these three limits are all going to be the same number. So we say that that number is the area under the graph of f from x equals a to x equals b. That's actually our definition of the area underneath a curve. It's not like the area underneath the curve was some mysterious thing and now we found that it is this thing. We're actually using this theorem that says that these three things all have the same limit to define the area to be that common limit. Areas, really, all we know is areas of rectangles. That's the only thing that kind of makes base sense, Everything, all other areas are defined in terms of limits of areas of rectangles. That's how it works in mathematics. Well, I should point out the f does need to be non-negative on the interval for this to make sense. I mean, if f dipped into the negatives like this graph does here, then there isn't really an area under the curve, because we're always meaning under the curve and over the x-axis. There's still some point to thinking about rectangle approximations for this kind of a picture, but we'll deal with that in a later section. For now, assume your f's are always bigger than or equal to 0 on the interval where we're working. So, hey, could we go ahead and find that shaded area exactly instead of just approximating it? Well, by definition, all we got to do is take the limit as capital N goes to infinity of maybe the RNs or the LNs or the MNs. It doesn't matter which one we decide to work with. Well, if I'm going to do that, I need to think first about what it means to divide up into capital N pieces instead of just 4 pieces or 6 pieces or 20 pieces or 27 pieces or whatever. So take that interval from 0 to 2 and imagine it divided up into capital N pieces. So I've got the interval written out here. And I've got 0, the beginning, so I could call it A. I could also call it x0. Now I've got 2 at the end, so I can call it B, and it's going to have to be x capital N as well. And I've broken into n pieces, so my delta x, which is always my b minus a over n, is 2 minus 0 over n, so the delta x, the width of each of these intervals, is 2 over n. So I could write down what the x1 is. I could say, well, it's 0 plus 2 over n. I could write down the x2. It's 0 plus 2 of these 2 over n's, 2 of these delta x's, so I could say 4 over n. Similarly, this is x3 and x4, and I could keep going like that. And for clarity, I'm going to look at the third to the last, okay? So this is my xn minus 2. Here's my xn minus 1. Here's my x capital N. Xn minus 2 must be the a plus n minus 2 of those delta x's. The a was 0. The delta x was 2 over n. And so this is what that point is. Here's the xn minus 1. In similar way, it comes out to this. And let's see if it all works out. This should be the a plus n of those delta x's. So it's 0 plus n of those 2 over n's. So it is n times 2 over n. It is 2, just like it's supposed to be. We're happy. Everything's checking out. Okay, so I've got the division really clear in my mind. I've got the n rectangle bases, and I'm looking at them. And I've got a clear idea of what the left and the right-hand endpoints for these rectangle bases are. So next thing I'm going to do is I'm going to pick a strategy. Do I want left? Do I want right? Do I want middle? I'm going to pick right. So I want to find the limit as n goes to infinity of Rn. In general, that's limit as n goes to infinity, delta x, that's sum. Okay, the delta x is 2 over n. My f is x squared, so I've got to write my general as xi squared. Now, it's going to help me in my thinking to write that sum out in the non-closed form with dot, dot, dots. So I'll write x1 squared plus blah, blah, blah to xn squared. Don't forget, you still have your 2 over n, and you're taking the limit as n goes to infinity. So I keep that part tagging along, even though I'm right now focusing mostly on what's in there. Now, I've got the pattern down for what those xi's are, you know. Here's the x1, I square it. Here's the x2, I square it. All the way up to the xn minus 1 squared and the xn squared. And notice I'm kind of perversely writing out the pattern way of expressing the number rather than the simplified way, because I want to keep that pattern in mind. When I keep that pattern in mind, I see the general term is twice a number over n squared. 2i over n squared, I going from 1 to n. Now I can start just using facts about arithmetic, like that, the distributive property, for instance. Well, no, wait. Let me hold on and just do something. Let me square that out. So when I square that out, I get 2 squared times I squared on top, and I get n squared on bottom. Now let me start using my arithmetic facts. Distributive property. Think about like the 4. That's the same in each of those terms we're adding up. So I could just pull it out by the distributive property outside the sum. And this 2 times that 4 is 8 outside the sum. Similarly, this 1 over n squared that I've got, that's a constant. I can factor it out of the sum, and I'm combining it a little bit with the 1 over n factor outside. And so I'm left with the sum of the squares of the first capital N whole numbers, which I happen to have a formula for. And so I just got to find the limit of all that mess. Now that's moderately scary, but don't worry. 8 over 6 at least does simplify to 4 over 3. And n divided by this n cubed simplifies to have just an n squared on the bottom. I still got I should probably just multiply out the n plus 1 times the 2n plus 1, see if anything comes out of that. Here's the foiling out result. And then I think, you know what? I can do limits of this kind of fraction. The top is going to infinity because n's going to infinity. The bottom's going to infinity as well. But they both go about as fast as n squared does. I'm going to divide the top and the bottom by n squared. This is a trick you probably learned back in Calc 1. When I divide the top and bottom by n squared, I'm not changing the quantity I want to find the limit of, but I'm sure making it more convenient to analyze. There we go after dividing the top and bottom by n squared. I can now let the n go to infinity in my mind. And I see that 3 over n going to 0. I see the 1 over n squared going to 0. So I see 4 times 2 plus 0 in the limit. Over 3, of course. So I see 8 over 3. 2.666666 repeating is the exact sum, is the exact area underneath this curve. So sure enough, the midpoint approximation was pretty accurate. Okay, so we can actually use this this idea to try to find areas underneath the graphs of lots of different functions. We'll have to have formulas for the first capital N terms of some pattern sum that matches our function if we have a hope of applying this method. So there's not a whole lot of functions that we can apply it to. But there's quite a few. But you're probably wondering by now, like, why is it important to be able to find the area under the graph of the function? Well, here's one reason that the textbook gives and that I want to emphasize too. Think about this old formula. Distance is rate times time. The distance you travel is the speed you travel at times the time that you spent traveling at that speed. The rate here is more formally called velocity. So for example, if your velocity is 30 feet per second and you go at that velocity for 2 seconds, multiply these out, the seconds will cancel. The 2 times 30 is 60, so you went 60 feet. Now, you could think of that 60 feet as the area of this rectangle here that I have drawn on a plane where I've got a t-axis, where t is time measured in seconds, and I've got a velocity axis where velocity is measured in feet per second, and I'm going from time 0 to time 2 and keeping a constant velocity over that time. So this horizontal line that I'm moving my cursor over here, that horizontal line is the graph of my velocity as a function of time, okay? And that rectangle there is what's under the graph. The area under the graph is, look at it, 2 times 30, base times height, 60 feet. The area under the velocity function makes the distance traveled amount, okay? So it stands to reason that if you're in another situation where instead of being at a constant velocity, if your velocity changes in some continuous way over time, like here, say the graph of your velocity was this curvy thing, okay? So say there's y equals v of t. From some beginning time to some end time is what you're interested in. That the area underneath that curve should be considered to be the total change in your position from the time A to the time B. And so you could approximate it using any of these methods you like maybe your right-hand rectangles or your left or your midpoints. As long as you choose a big capital N so that you're looking at a lot of rectangles, those rectangle tops will be pretty close to the curve, and so the total area of the rectangles won't be too far from the area under the curve. You know, basically, when you're looking at, say, this situation here, it's like you're temporarily assuming that your speed stays constant over these short little time intervals, like it's constant, and then jumps to be another constant, and then it jumps to be another constant, and so on. And so under that situation, your speed is never exactly what it was, really. It's just an approximation. But the area underneath the curve over each of these bases can't be very different from the area underneath the rectangle. And so this ought to be a good approximation if the capital N is large. And if you take the limit as n goes to infinity, you ought to get the distance traveled exactly, the net change in your position exactly. And it doesn't just work for velocity figuring out net change in position. Actually, it turns out it works any kind of situation where you're wondering, what's the net change in a quantity? Like, what is it at the end minus what it is at the beginning? That's called the net change in a quantity. To find the net change in a quantity, just think of a graph of the rate of change of the quantity. Remember, derivative is a rate of change? If you could take the derivative of a formula for your quantity to get its rate of change, make a graph of that, and get the area under the graph of that, you will figure out how much the quantity changed. So this is widely applicable, and it's why areas underneath curves are so important. To round things off, let me just do a couple of sample exercises. We'll do many more to practice together. But what if you were looking at this limit as capital N goes to infinity? It represents the area underneath some curve from some beginning number to a stopping number. Could you figure out what it is? There's a couple of different ways to set it up in your mind. But the way I'm thinking is I look at this general term here, and it kind of reminds me, it's like e to minus something that stays the same, plus something that's changing because the j is changing. So it kind of reminds me of this function, f of x is e to the negative 2 plus x. Is there a way that we could represent this limit here as an area underneath this curve? Well, let me see. When j is 0, I'm looking at e to the negative 2. If j is capital N minus 1, that's almost a capital N, so I get basically a 5 out of here. You know, could I think of the x here as going from 0 to 5. So I'm going to set up on the real line 0 to 5, and I'm going to imagine breaking that interval up into capital N intervals. So my delta x is 5 over n each time. And, you know, my 0 is x0. The x1 is 5 over xn. The x2 would be 0 plus 2 times 5 over n, and so on. My xn minus 1 would be 0 plus n minus 1 times 5 over n. And then my 5 would be the 0 plus n 5 over n. So, you know, when I think about it that way, I realize, whoa-ho, that is delta x, and this is the sum of the left-hand endpoints for rectangles over those bases that I'm showing here underneath that curve. This sum exactly fits this. So when we look at its limit, we're looking at the limit of these LNs. And we know that by definition that goes to the area underneath the curve. F of x is e to the negative 2 plus x. X goes from 0 to 5. So that's one way to represent this as the area underneath a curve. There's actually, you can represent it as the areas underneath other curves, and they all look kind of like an e to the x. You would just have to have different beginning and end points. But this is just one way to do it. One little last exercise. Say you got a big pattern sum. M goes from 1 to 30, 4 minus m cubed. Is there a way to find it exactly using stuff we already know? Well, I look at it and I think, well, I do know how to find sums of cubes and squares and whole numbers. Maybe there's a way to kind of bring that knowledge in. But the 4 over m part, that's what's different from the facts that I know so far. So I'm going to cube 4 over m. I'm going to cube out 4 minus m. So I think, well, how would I cube a difference anyway? How would I cube x minus y? Well, y'all may remember that to raise to powers, you can use Pascal's triangle to grab your coefficients. And if I go down to this row here that has the 3 in it, then that gives me coefficients. And the cubing out terms to be x cubed minus 3x squared y plus 3xy squared minus y cubed. So if I need this, I should look at the cubing out. And so here the x is a 4, 4 cubed is 64. 3 times a 4 squared is 3 times 16 is 48. And then here's my y to the 1. It's an m. My y is the m. And then here is a 3 times my x, 3 times 4, and my y squared, m squared. And then we're rounding off with the minus y cubed part. Now I'm going to use some commutativity and multiplication and stuff, because I'm just going to gather like the sum of these 64s together, and the minus the sum of the 48m, and I'm going to factor out the 48. And similarly, I'm going to gather these together and factor out the 12. And I'll just leave the minus sum of the m cubes at the end. And hey, this here, the general term does not even involve the index m. It's just 64 each time. So that means that I'm adding up 30 64s. 30 times 64. This bit is the n times n plus 1 over 2. So m times m plus 1 over 2 times the 48. This bit was the m times 2m plus 1 times, m times m plus 1 times 2m plus 1 over 6. 12 times it. Let's check. Is that what it was? Let's just check. Go up, find our formulas. They're in the book too, by the way. Yep, that's what it was. Okay, so, and lastly, the sum of the first 30 cubes is the square of the sum of the first 30 whole numbers, capital N times capital N plus 1 over 2 squared. So you could simplify that out, or you could, get it in a calculator or something like that. But the main idea is that you can get it by using the simple summation formulas for whole number squares and cubes, plus a little bit of arithmetic facts. Okay, that's it for now. I will see you again soon. Bye-bye.